Fine. Let's start. The danger zone for a supernova is roughly 26 light years. The nearest star to us is 4.25 light years away. On paper, we're fine. We're well inside the safe zone. Nothing on the current map should be able to reach us. This video is about why that comfort is more complicated than it sounds. Number 10. Proxima Centauri. The closest star to our solar system is 4.25 light years away. That's close, astronomically speaking. Close enough that we've already found a planet orbiting it. An Earth-sized world sitting right in the habitable zone. The region where liquid water could exist on the surface. In March of 2016, Proxima Centauri erupted. It released a superflare, a burst of energy about 10 times more powerful than anything we'd ever seen from it before. For a brief window, this tiny red dwarf star, normally too dim to see without a telescope, became briefly visible to the naked eye from dark sky sites on Earth. We were standing in our backyard, essentially, watching the nearest star in the universe detonate. And here's the thing. That flare delivered roughly 100 times the ultraviolet radiation required to kill even UV-resistant microorganisms to the surface of that orbiting planet. Not 100% over the threshold. 100 times it. If anything was living on Proxima b during that moment, the math is not encouraging. Now, we're fine. 4 light years is enough distance that the flare barely registered here. But that planet, that Earth-sized world in the habitable zone of our nearest neighbor, is getting hit by events like that roughly 5 times a year. Every year. The ozone layer of any Earth-like atmosphere there would be permanently stripped within about 5 years of continuous bombardment. The closest star to us is not a quiet, stable sun. It's a radiation machine on a hair trigger. And it's the most peaceful thing on this list. Number 9. Eta Carinae Borealis. Somewhere in the constellation Coronae Borealis, the Northern Crown, there is a small, faint smudge of light that you cannot see without a telescope. It sits between the bright star Arcturus and the constellation Hercules. Magnitude 10. Totally invisible to the naked eye. That's about to change. Eta Carinae Borealis is a recurrent nova, a binary system, a white dwarf and a red giant locked in orbit, where the white dwarf slowly steals hydrogen from its companion, builds it up on its surface over decades, and then ignites it in a thermonuclear explosion. Every 80 years or so, roughly on schedule, it blows. And when it does, it goes from magnitude 10 to magnitude 2, temporarily rivaling the North Star in brightness, visible from cities, visible from anywhere with a clear sky. The last confirmed eruption was February 9th, 1946. 80 years from 1946 is 2026. Most astronomers have been watching it since 2023, when it began showing the same pre-eruption dimming pattern that preceded the 1946 event. The prediction was September 2024. That passed. Then late 2025. That passed too. As of right now, it still hasn't gone. But it will. The white dwarf is confirmed to be accreting mass at an increased rate. The spectral lines are strengthening. Something is coiling. What makes this one worth pausing on isn't the explosion itself. At 3,000 light years, it's completely harmless. What makes it worth pausing on is a detail buried in the historical record. The earliest confirmed observation of this star's outburst wasn't in 1866, when modern astronomers first cataloged it. It was in the autumn of 1217, when a German abbot named Burchard, abbot of Erzberg, Bavaria, wrote in his chronicle that he had observed a faint star that for a time shone with great light. He had no idea what it was. He had no framework for it. He just wrote it down and moved on. 800 years later, we know exactly what he saw, and the same star is about to do it again, for the first time in living memory, and we're watching it like we're waiting for a kettle to boil. Number 8. RS Ophiuchi. On August 8th, 2021. A Brazilian amateur astronomer named Alexandre Amorim pointed his camera at a patch of sky in the constellation Ophiuchi and noticed something wrong. A star that was normally magnitude 12, invisible without serious equipment, had jumped to magnitude 5, about 600 times brighter than it should have been. He sent an alert. An Irish observer named Keith Geary confirmed it 25 minutes later. What they'd caught was RS Ophiuchi going nova. Again, the system had erupted in 1898, 1933, 1958, 1967, 1985, 2006, and now 2021. 7 documented explosions. A white dwarf feeding off a red giant companion, periodically hitting the limit, detonating, and surviving to do it again. What made the 2021 event different was what the big telescope arrays detected afterward. The Magic and Hess gamma ray observatories, massive ground-based facilities designed to catch the highest energy light in the universe, picked up gamma rays from RS Ophiuchi at energies up to 250 gigaelectron volts. That was a first. No nova had ever been detected at that energy level before. The shockwave from the explosion was accelerating protons to speeds we hadn't seen from a system like this. And here's the thing. The white dwarf at the center of RS Ophiuchi has a mass very close to the Chandrasekhar limit. 1.4 solar masses, the threshold beyond which a white dwarf cannot hold itself together and will detonate in a full-type Aya supernova. Scientists have been arguing for years about whether this system is slowly gaining net mass toward that limit, or whether each eruption ejects more than the white dwarf accretes in between. The honest answer is, science currently cannot say. Nobody knows if RS Ophiuchi is counting down or slowly disarming. The system erupted 4 years ahead of its expected schedule in 2021. The thing about a gun you can't predict is that the unpredictability is the problem. Number 7. Antares. Go outside tonight, if you're in the northern hemisphere, and look south. In the constellation Scorpius, you'll find a reddish star, distinctly, unmistakably red, like an ember, sitting at the heart of the Scorpion. That's Antares, 550 light-years away, 12 to 14 times the mass of our Sun. So large that if you replaced our Sun with it, it would swallow Mercury, Venus, Earth, Mars, and extend past the asteroid belt. It is going to explode. Astronomers are essentially certain of this. The estimated timeline is somewhere between 1 and 1.4 million years from now, which is soon in stellar terms, and long after we're gone in human terms. When it goes, it will be as bright as the full moon for several months, visible in daylight. Now here's the detail that earns Antares its place on this list. Its companion star, Antares B, a blue-white star orbiting nearby, shows unusual spectral lines in its atmosphere, chemical signatures that shouldn't be there for a star of that type. The explanation astronomers have settled on: Antares has been flinging material at its companion for so long that Antares B's outer atmosphere has been contaminated by it. You can read the violence of Antares in the chemistry of its neighbor, like finding someone else's shrapnel embedded in a bystander's skin. But the deeper reason Antares is on this list is context. Antares isn't just a lone supergiant doing its thing. It's a member of the Scorpius-Centaurus OB Association, a loose cluster of massive young stars between roughly 300 and 500 light-years away. And that cluster has been exploding for millions of years. At least 14 to 20 supernovae from Scorpius-Centaurus have gone off in the last 10 to 15 million years. We have the receipts. Radioactive iron, iron-60, found in deep-sea sediments, in Antarctic snow, on the lunar surface, inside fossilized bacteria, all bearing the chemical fingerprint of those explosions. The most recent major spike in that iron-60 record coincides with about 2.6 million years ago. That's also when the megalodon disappeared, along with a significant fraction of large marine animals. Researchers at the University of Kansas have proposed that a tsunami of muon radiation, subatomic particles that penetrate seawater, that penetrate flesh, rained down on Earth from those supernovae and preferentially killed the largest ocean creatures. Antares is the next round in that same gun. It just hasn't been fired yet. Number 6. IK Pegasi. IK Pegasi is a binary star system in the constellation Pegasus. It's about 150 light-years from Earth, close enough to be visible to the naked eye under good conditions, though you'd have no reason to look at it twice. It is the nearest known candidate for a Type Ia supernova in the Milky Way. Type Ia supernovae are the most precisely dangerous kind, not just because of raw energy, but because they're detonations, not slow collapses. A white dwarf that crosses the Chandrasekhar limit doesn't gradually fail. It explodes completely and catastrophically, converting a large fraction of its mass to energy in a matter of seconds. The ozone-destroying threshold for a Type Ia is estimated at around 25 to 26 light-years. IK Pegasi is at 150, which means it's outside the kill zone. Just. Not comfortably, but outside. And it won't explode for roughly 1.9 billion years. By then, it will have drifted farther from us anyway, carried by its velocity relative to the Sun. So why mention it? Because of what it implies. IK Pegasi is the closest Type Ia candidate we know about, but Type Ia supernovae come from white dwarf stars in binary systems. White dwarfs are small, roughly the size of Earth. They emit mostly ultraviolet and X-ray light. In a binary system with a dim companion, they can be extraordinarily hard to detect. We've cataloged the obvious ones. What we haven't cataloged, what we can't catalog, are the unremarkable ones. The faint, dim, ordinary-looking binary pairs that nobody's studying because there's no reason to. The one that could actually matter might not be on any list. The star that could threaten Earth from a Type Ia event probably looks, right now, like nothing in particular. Number 5. Eta Carinae. In 1843, the second brightest star in the night sky was a star called Eta Carinae. Not Sirius, not Canopus. Eta Carinae, a star 7,500 light-years away, that, by all physical rights, should have been a faint smudge in a telescope. Instead, for several years around that period, it outshone everything except the Sun itself, and was visible in broad daylight. It hadn't exploded. Not fully. What happened was what astronomers now call a great eruption, a violent instability in the star that caused it to shed mass at an extraordinary rate and briefly shine with the luminosity of 5 million suns. Eta Carinae is over 100 times the mass of our Sun. It is the most massive and luminous star known in the Milky Way, and it is approaching its end. When it finally goes, and scientists believe it could go at any time on a cosmic scale, it won't be a standard supernova. The leading model is a hypernova, a collapse so energetic that it would release gamma-ray bursts along its polar axis, each one carrying the entire energy output of our Sun over its 10 billion year lifetime, compressed into a beam lasting seconds. Scientific American laid out the worst-case scenario plainly. A direct hit from a gamma-ray burst originating at Eta Carinae would be, in their words, similar to, but far worse than full-scale thermonuclear war. The hemisphere of Earth facing the star would receive a burst of high-frequency radiation energetic enough to ignite continent-scale wildfires. The skies would be brighter than the Sun for several searing seconds. The ozone layer on that side of the planet would be stripped. The reason we are probably safe is that Eta Carinae's rotational axis is tilted roughly 45 degrees away from Earth. Gamma-ray bursts travel along the spin axis, so the beam, if it forms, would miss us. Probably. That 45-degree tilt is derived from observations of the surrounding nebula and historical outburst patterns. It hasn't been directly confirmed with the precision you'd want when the stakes are continent-scale wildfires. And there's a second detail that doesn't get much attention. Even without a direct GRB hit, if Eta Carinae explodes like SN 2006 GY, the brightest supernova ever recorded at the time, which may have had a similar progenitor, the resulting months of intense blue-shifted light reaching Earth would disrupt circadian biology, hormonal cycles, and photosynthesis in organisms on the hemisphere facing it. Not an extinction, but not nothing. Eta Carinae already erupted once, 200 years ago, hard enough to be the second brightest object in the sky. That was a hiccup. The main event is still coming. Number 4. WR-104. In 1999, astronomer Peter Toothill of the University of Sydney was studying a strange object in the constellation Sagittarius, using the Keck telescope in Hawaii. What he found was a pinwheel, a perfect rotating spiral of dust and gas, spinning like a cosmic pinwheel toy, completing one full rotation every 8 months, keeping precise time like a jewel in a cosmic clock, as he described it. It was beautiful. And then he realized what it meant. The pinwheel's shape. Specifically, the fact that it appeared as a nearly perfect circle when viewed from Earth, indicated that we were looking almost directly down the axis of rotation of the binary system at its center. We were staring into it, like looking down the barrel of a gun. And one of the 2 stars in that system was a Wolf-Rayet star. A Wolf-Rayet is a massive star in its final phase before a supernova, extremely hot, shedding mass at a ferocious rate, burning through its fuel like an engine running at full throttle with the governor removed. Wolf-Rayet stars produce long-duration gamma-ray bursts when they collapse. Those bursts travel along the rotational axis. The rotational axis of WR-104 appeared to be pointed almost directly at us. Toothill put it this way: I used to appreciate this spiral just for its beautiful form, but now I can't help a twinge of feeling that it is uncannily like looking down a rifle barrel. The press called it the Death Star. Scientists were more cautious, but the concern was real enough that University of Kansas physicist Adrian Mellett calculated the impact of a direct hit, a 50% increase in ultraviolet radiation reaching Earth's surface. Not immediately lethal for the planet, but deeply damaging to ecosystems, and particularly to marine food chains. Then, in March of 2025, a new study from the Keck Observatory was supposed to close the case. Astronomer Grant Hill spent years measuring the velocities of both stars in the system, and finally confirmed that the orbit of the binary pair is tilted 30 to 40 degrees away from us, not face-on as the pinwheel had implied. The burst, if it formed, would miss Earth. Case closed. Except, the study also revealed something that nobody expected, and nobody can currently explain. The dust spiral, the pinwheel, appears face-on, as if we're looking directly down on it. The stellar orbits are tilted 30 to 40 degrees. Those 2 things are describing the same system and pointing in completely different directions. The geometry is contradictory. Hill himself said, "We may answer some questions, but create more." The Death Star label has not been officially retired. What has happened is that the thing we thought we understood about WR-104 turned out to be weirder than the original threat. It's 8,000 light-years away. It probably won't kill us, but nobody has fully explained it yet, and it hasn't exploded yet, and the axis discrepancy remains open. Number 3. Geminga. 300,000 years ago, a star somewhere in what is now the constellation. Gemini collapsed and exploded. When the light reached Earth, early Homo sapiens and Neanderthals were both alive. The sky would have held a new star, brilliant, burning, alien, for weeks or months before fading. We never found a written record of it. We found something better. We found where we are. The solar system currently sits inside a region of space called the local bubble. It's a cavity in the interstellar medium, the thin gas and dust that fills the space between stars, roughly 1,000 light years across, filled with unusually hot, low-density plasma. The edges of the bubble are a shell of compressed material, like the wall of a soap bubble. The inside is clear. That bubble was blasted open by supernovae. Multiple ones, from the Scorpius Centaurus cluster and from the star that became Geminga, a star that exploded roughly 250 to 800 light years from where our solar system was at the time. The Geminga supernova, along with the cascading explosions in Scorpius Centaurus, hollowed out the neighborhood we now live in. Geminga's remnant, the pulsar it left behind, is today the closest known pulsar to Earth, still spinning, still spraying high-energy particles into the surrounding space. Physicists studying the mysterious excess of positrons, antimatter electrons, being detected in cosmic rays near Earth by the Fermi Space Telescope and the Alpha Magnetic Spectrometer aboard the ISS, have pointed at Geminga as a probable source. 300,000 years after its death, the star is still affecting the particle environment around Earth. In 1993, physicist John Ellis from CERN and cosmologist David Schramm from the University of Chicago published a paper in which they asked plainly whether the Geminga supernova or ones like it could have caused mass extinctions. Their calculation: a supernova within roughly 33 light years could destroy the ozone layer for hundreds of years. Geminga was probably not that close, but it carved the bubble we're inside right now. We don't just live near the sites of these explosions. We live in the wound they left. The local bubble is our address, and it's a scar. Number 2. SGR 1806-20. December 27th, 2004. 50,000 light years away, on the far side of the Milky Way, closer to the galactic center than we are, a neutron star suffered what scientists call a catastrophic reconfiguration of its magnetic field. In simpler terms, it had a starquake, and it released more energy in 0.2 seconds than our sun will emit in 250,000 years. The object is called SGR 1806-20. It is a magnetar, a subclass of neutron star with a magnetic field so intense it holds the record as the most highly magnetized object ever directly observed. Its field strength is over 10 to the power of 15 Gauss. The sun's magnetic field runs between 1 and 5 Gauss. Earth's is less than 1 Gauss. The energy from the December 27th flare was so extreme that it briefly outshone the full moon in gamma rays for 0.2 seconds before fading. For that fraction of a second, it was brighter than any transient event previously recorded from outside our solar system, and it physically disturbed Earth. The burst of gamma and X-ray radiation ionized the upper atmosphere, the ionosphere, on the side of Earth facing the source. That ionization was picked up simultaneously by satellites and monitoring stations around the entire globe. Researchers at Germany's Geoforschungszentrum in Potsdam later published a paper showing the event left a measurable signature on Earth's magnetic field as detected by near-Earth satellites. A star 50,000 light-years away reached across the galaxy and nudged our atmosphere. 5 papers about this event were published simultaneously in the journal Nature in April of 2005. The total energy of the flare, 2 × 10 to the 46th ergs, was roughly 100 times more powerful than the only 2 previous magnetar giant flares ever recorded. Scientists called it a once-in-a-century event, possibly a once-in-a-lifetime event for the star itself. The Wikipedia entry for SGR 1806-20 notes, without drama, that a similar blast within 3 parsecs, 10 light-years, of Earth would be similar in effect to a 12-kiloton nuclear blast at 7.5 kilometers, and would destroy the ozone layer. The nearest known magnetar is 9,000 light-years away. We know of about 30 magnetars total. There may be many more we haven't found yet. Distance is supposed to be the thing that saves us. A star 50,000 light-years away affected our planet in a way that was measured with instruments. Not catastrophically, but measurably. There is no version of that fact that should make you feel completely relaxed. Number 1. The Ordovician extinction. 445 million years ago, roughly 2/3 of all species on Earth disappeared. This is known as the Late Ordovician mass extinction, the second largest in Earth's history, behind only the End Permian event that nearly sterilized the planet entirely. Life at this point was mostly ocean-based. The seas were full of trilobites, brachiopods, cephalopods, coral, early vertebrates, and then, geologically speaking, most of them were gone. The established explanation was an ice age, an abrupt cooling event triggered by changes in ocean circulation and perhaps by volcanic activity. It's a reasonable answer. It fits some of the data. In 2004, a team led by University of Kansas astronomer Adrian Malott, along with researchers including scientists from NASA's Goddard Space Flight Center, published a paper in the International Journal of Astrobiology proposing something different. They proposed that a gamma ray burst from within 6,000 light-years of Earth struck our planet for approximately 10 seconds. In those 10 seconds, the burst stripped away roughly half of Earth's ozone layer on the hemisphere facing the source. Ultraviolet radiation from the sun, normally filtered, normally manageable, flooded the surface and shallow waters. What followed was a cooling event, as nitrogen oxides formed in the destroyed atmosphere, reflected sunlight, and dropped global temperatures dramatically. An ice age. The same ice age that traditional models struggle to explain the sudden onset of. The gamma ray burst would explain both. Here's the detail that makes this genuinely unsettling. The fossil record of the Ordovician extinction doesn't just show mass death. It shows a specific pattern. Shallow water organisms and surface-dwelling life died in far greater proportions than deep-water species. The organisms that lived in shells or burrowed below the sediment survived at higher rates. The organisms most exposed to UV radiation, the ones living at or near the ocean surface, were preferentially wiped out. That is exactly what a hemisphere-scale UV event would produce. One side of Earth hit, the other side relatively spared. The survivors clustering in whatever shadow they could find. The fossils are, in a very real sense, showing us the shape of something that hit this planet 445 million years ago. And in 2025, a team at Kiel University published a census of massive stars within a few thousand light-years of Earth and calculated the rate at which nearby supernovae should occur. They found that the rate is statistically consistent not just with the Ordovician extinction, but with the late Devonian extinction as well. Another major die-off about 372 million years ago, which killed roughly 70% of all species. We may have been hit twice. The star responsible for the Ordovician event left no known remnant. It existed, it fired, and it is gone. We don't know its name because it never had one. We don't know exactly where it was. We only know it by the absence it created, in the fossil record, in the sudden drop in species diversity, in the strange geographic pattern of who survived and who didn't. Every other star on this list has a name, a location, a catalog number. We can point at it. We can measure it. We can argue about whether its axis is tilted at 45 degrees or 30 degrees and what that means for us. This one is just gone. Which means the question isn't really about the stars we can see. It's about the ones we can't. The ones that look unremarkable from here. The dim binary that isn't in any catalog. The magnetar we haven't found yet. The future burst from a direction we're not watching. Every star on this list, by current measurements, is either too far away or pointing the wrong way, or billions of years in the future. We're safe, for now, from everything we can identify. The Ordovician killer suggests that everything we can identify might not be the right category to feel safe inside. The universe has already done this to us. We found out about it 445 million years later, from the shape of the dead things left behind, and we wouldn't have known it was coming. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.